Joy. I'm the 8th. Have you?
Crazy guy. Come on. Playing too much.
I can exit now. You see me now. Bye-bye.
Thank you very much. So have you made me the
You are the host.
So it's streaming now. Thank you very much. Everybody, please, can you please mute your display? Mute your mic, please.
What I drew for you.
Mute your mic.
Can only accommodate 30%.
I think we can start the class now.
Are you done?
I don't get it. What do you mean? Two, four. I don't know. So. Oh, my brother. I'm at the busy man. What do you mean discuss? What do you mean discuss? No, man.
Oh yeah, now let's start. Everyone stand up. Everyone stand up. Oh. Who is not in the class? Who is not in the class? He tried. Oh yeah.
So now the teach.
Oh yeah. What's this?
Mute your mic. Mute your mic.
Now.
Nah.
If I want to the guy,
Mutia. Moi, ça relève quand même, mais tu m'as équipé.
5, 5.
Mama, off your camera.
Dr. please make me co-host so I can share
You're
my
already the
slides.
host. You're already the host. You're already the host, man.
I'm not
You're
seeing
already the
myself
host.
as host. I can only see you as I see you as also. I'm not host. It's
Check
not
it.
allowing me to share.
Check it, man.
You are the host. I'm looking at it. I say I'm looking at it. Do it again. I don't know what's wrong with Zoom.
Okay.
You say I cannot. Yeah. This is part of the frustration of this thing. I see you as host here.
I've already done it. You're host. So I'm saying it like.
Okay, I just became host right now. Before
Okay.
it wasn't. Thank you.
All right, man.
So I hope it's not going to push me out again.
No, maybe it's the network that cut you off in your internet.
So I should share the YouTube this thing you sent to me, Abi.
Yes, exactly. It's online. It's streaming right now.
Okay, I will share it to them now. Thank you. Thank you so much. So thank you for your patience, everybody. It's part of the things we see when we are doing online. So I've sent for anybody that couldn't enter, please I've sent the YouTube link. I sent it to the platform, so you can do it. So okay, so let me continue. We have already wasted a lot of time. So as I said, we are going to look at the chemical properties of alcohols based on two parameters: the cleavage at R and the CO, and the cleavage at OH. So the cleavage at CO, I said, is going to give us an alkoxide ion, which is a conjugate base. And the acidity depends on how the conjugate base can accommodate negative charge, because the alkoxide ion will carry the negative charge, and the proton, which is the hydrogen that is cleaved off, will carry the positive charge. So any factor that stabilizes the alkoxide ion stabilizes the alcohol. And so that will increase the acidity. And the other way around also. That is, anyone that destabilizes reduce the alcohol. So the electron withdrawing substituents on the alkyl group that is attached to the OH disperse the negative charge and stabilizes the RO, and this also increases the acidity. So when we have electron withdrawing group on it, it's a positive thing because it's going to stabilize the alkoxide ion. Then the acidity of alcohol is shown by their reaction with active methods to give hydrogen and methoxide, just like the activity of the normal, you recall that the normal mineral acid, when you react them with acid, it always shows their acidity, the strength of the acidity. The same thing with alcohol, because it can act as an acid. If we react NaCl, you find out that it reacts with the form sodium ethoxide, which is what we have in this reaction. Sodium ethoxide, hydrogen is given off as a gas. So that is even one of the tests for the acidity of these compounds. And also, an alcohol as a base accepts proton. You know that an alcohol as a base gives off proton to give alkoxide and a proton. But an alcohol as a base accepts proton using a lone pair of electrons on the oxygen. So it uses the lone pair of electrons on the oxygen, it accepts proton. And so by doing that, it reacts most rapidly with hydrogen iodide and hydrogen chloride, which requires the presence of zinc chloride most times. The zinc chloride is actually going to act as a catalyst when this reaction is occurring, because Hi and HCl are actually acid now. So it is the alcohol that is now going to act as a base. So this reaction can actually be used to identify differences in alcohol classes. You know, in the last class, I told you that we have 3 different classes of alcohol. We have the primary, we have the secondary, and we have the tertiary alcohol, depending on the number of hydrogen that is carried by the carbon that is having the OH. So this reagent HCl in zinc chloride is actually called the Lucas reagent. So it's a reaction that is used to test alcohol. Then when you going on to reactions with alcohol, so reaction of alcohol with HCl, chloride is a weaker nucleophile than bromide. So when you add zinc chloride, it bonds strongly with the OH and promotes the reaction. So the chloride product is always insoluble. When you get to the practical class, you are still going to do all these things, all these tests for primary, secondary, and tertiary. In your practical class, when you move in for primary, secondary, and alcohol, when we add Lucas reagents to the alcohol, and the alcohol is a primary alcohol, it will react slowly or not at all. If it is a secondary alcohol, within 5 minutes, between 1 and 5 minutes, the reaction occurs. We see changes. And then you see a solid, because the chloride is insoluble anyway, so you see solid being formed. But for tertiary alcohol, it reacts spontaneously. Within a minute, you see the reaction. So that is how we differentiate between primary and secondary and tertiary alcohol in the laboratory, which you are going to practicalize by yourself during the practical class that we are going to move into in the next few weeks.
Hey, again.
Make now buy spectranate for this one now.
I'm sorry, I don't know what is happening with my internet. This is my third class today, and all the other 2 classes went smoothly. And now I cannot even share because I'm not the host. Adeleye Solomon. The Zoom has made you host. Please, can you make me host back? Adeleye Solomon. Adeleye Solomon, the Zoom made you the host. Please make me host back. That's what Zoom does. Adeleye Solomon. Can you please make me host? Thank you.
Oh, yeah. Oh. You should just cancel the class.
I can hear what you are saying. So, this is the Lucas reagents we are talking about. So, this is the tertiary alcohol. This is the Lucas reagent that is concentrated HCl in zinc chloride at room temperature. It will react immediately with tertiary. It will react between 1 to 5 minutes with secondary, and it will be very slow or will not even react at all if it is a primary alcohol. And then you also have to even apply it. Then how does it react with the inorganic halides? Inorganic halides examples are the phosphorus pentachloride, phosphorus tribromide, or thionic chloride that we have here. We have the 3 of them here. The first reaction here is reaction of propanol with phosphorus pentachloride, and it forms an alkyl halide. It forms an alkyl halide. And then the second one with phosphorus tribromide also forms an alkyl halide. The third reaction of propanol with thionic chloride, this thionic chloride, SOCl2, also forms alkyl halide. So this is actually a reaction of alcohols, but they are also used to prepare alkyl halides. So we always have, you see the byproducts that are formed there, but the major ones we need are the products of the alkyl halides. Then esterification reaction. When alcohols react with acid, carboxylic acid, ester is formed. The reaction is a slow reaction and is carried out in the presence of a catalyst because it is a slow reaction. The catalyst used is always sulfuric acid. You can also use a dry hydrogen chloride, but the most commonly used is a concentrated sulfuric acid. This is to speed up the reaction, and then also to remove the water and push the equilibrium to the right to make sure that the reaction occurs. You can also use it for isotopic experiments, which have established that the overall reaction involves, isotopic experiments have established that the overall reaction involves the loss of a proton from the alcohol are not from the hydroxyl group, which is what we have here. So the proton loss is not from the carboxylic acid, but from the alcohol. They have used isotopic experiments to prove this, that is the way the reaction occurs. So this is esterification reaction. This is an ester from there. Then the reactivity follows an order that is shown there. The order is that if it is at methanol has the highest reactivity, followed by primary, and followed by secondary, followed by tertiary. So that's the order of reactivity of esterification reaction, which means that tertiary alcohol gives the least speed for reaction of esterification. So esterification is not new to all of us, we know it. Then we also have oxidation. Of course, when you oxidize alcohol, you get compounds like ketone, aldehyde, carboxylic acids. So, and the reaction can be used to distinguish also the different classes of the alcohols, because the type of products we get from the primary alcohol is different from the type we get from the secondary and the tertiary. And oxidants commonly used include acidic potassium permanganate. Those reagents are also using the sodium dichromate. You can also use chromium oxide in pyridine. And calcium at the very. Then primary alcohols are oxidized to aldehydes, and prolonged oxidation results in the formation of carboxylic acid. So that means the reaction can occur in sections. When you first of all react primary alcohols to, when you oxidize it, it will give you aldehyde. But when you take the reaction further, so there is a way whereby in the lab, whereby you can terminate the reaction at the aldehyde stage, if that is what you want to get. But you can, and also depends on the molecule of the oxidizing agent that you are using. The number of molecules that you are using also matters. So you can terminate it at the aldehyde stage, or you can also take it to the carboxylic acid stage. That means primary alcohol can give you aldehyde, can also give you carboxylic acid. But what you have to know is that they have the same number of carbon atoms as the primary alcohol. That's what you get at the end of the day. So that means if you start with a propanol, you are going to end with a propanal or a propanoic acid. That's what you are going to get. And if you start with a butanol, you are going to end up with a butanal and a butanoic acid. When you use pyridinium PCC, pyridinium chlorochromate, it makes the reaction easier to stop at the aldehyde stage, because sometimes it might be very, very difficult. In fact, most times it's difficult for you to stop at the aldehyde stage. So the choice of oxidizing agents matters so much. So the choice of your oxidizing agent should be PCC. When you choose PPC as your oxidizing agent, which is pyridinium chlorochromate, it will limit the oxidation and you will get your aldehyde that you desire. But if you don't desire to get an aldehyde, you want to take it further to get carboxylic acid, then you can use Jones reagents or the potassium permanganate or the other ones. Then secondary alcohol is oxidized to ketone, and further oxidation leads to oxidative degradation. What do we mean by oxidative degradation? A degradation that cuts the molecule into pieces. It can cut it into 2 or it can cut it into 3. If you look at this pentanthol, the pentanthol, because it's a secondary alcohol, when you react it with chromium oxide, what we get is the ketone, which is pentanthol. So this pentanthol, on further reaction with the chromium, excuse me, with the oxidizing agent, you are going to now get, because it is now getting vigorous, it is more, you are adding more of the oxidizing agent. So what we get is a cleavage, which is now called oxidative degradation. So you get ethanoic acid, so it's cleaved into 2, ethanoic acid and propanoic acid. If you add in 2 numbers of the carbon, it is C5. What we started with is 5. What we ended up with is 5. But that means it depends on whether you want to do further oxidation or you just want to stop it at the alcohol ketone stage. So that is oxidation of secondary alcohol. Then for tertiary alcohol, they are generally resistant to oxidation. More so when you use them under neutral and alkaline conditions. Acidic solution can still help. Even then, they will also undergo oxidation degradation. They will degrade, even if you use acidic. So most times, tertiary alcohol are not oxidized because you don't get your desired products because they are too difficult to do. And you also have to put a vigorous oxidizing agent or condition, a vigorous condition by adding maybe sulfuric acid, concentrated acid, or whatever, and you will still not get, because it will cleave the compound, the alcohol, into two. It will degrade it, oxidative degradation, or sometimes they call it oxidation degradation. It's the same. So that's what we get for. So now we have discussed the oxidation. Now we have discussed oxidation. So let's talk about dehydration. From our knowledge in FSC 112, we know that dehydration will always remove a molecule of water. And when a molecule of water is removed from an alcohol, you automatically get an unsaturated compound, which is a carbon-carbon double bond. So like dehydrohalogenation, this is a beta elimination reaction in which the elements of OH and hydrogen are removed from the alpha and beta carbon atoms respectively. The first carbon is called the alpha, the carbon carrying the OH is called the alpha, the next carbon to it is called the beta. So that's why they call it alpha beta, so because OH is removed from the alpha carbon and hydrogen is removed from the beta carbon. So you remove this OH and it forms water. That's why we have elimination of water. And then what you have there is actually, when you go through the reaction mechanisms, this is an overall reaction. If you go through the reaction mechanism, you see that a new pi bond has been formed, so it becomes an alkene. So saturated compound now becomes an unsaturated compound. It is carried out in the presence of sulfuric acid, another strong acid. POCl3 can also be used in the presence of a base, which is an amine base. The typical acids used for typical acids that are used for alcohol dehydration are, like I said, are sulfuric acid and other types of acid. You can also use toluene sulfonic acid. So we have some examples here. The first example is the example of using two 2-methyl-propan-2-ol. This is 2-methyl-propan-2-ol. In the presence of sulfuric acid, you can see that what you are having here is an alkene. An alkene. Now, when you count the number of substituents here, you see that we have 2 substituents of methyl and 2 hydrogens here. And so this is what an elimination of water. And this is cyclohexanol. Cyclohexanol, in the presence of another type of dehydrating agent, which is a toluene sulfonic acid, p-toluene sulfonic acid. I believe you know the meaning of p-toluene sulfonic acid. Toluene is a benzene ring with a CH3, and then it has sulfonic acid attached to it, and to the para position of the benzoic acid. So p-toluene benzoic acid, we also change to an unsaturated compound, because water has been eliminated. Anytime water is eliminated, unsaturation comes in, and carbon-carbon double bond is produced, like we have here. So more substituted alcohols dehydrate more easily, giving rise to this order that we have: primary, secondary, and tertiary. Like I've said before, that's the rate of dehydration. The best dehydration rate is for primary, followed by secondary, and tertiary has the least dehydrates, the highest dehydrating rate, sorry, the highest dehydrating rate goes. Some people are talking and you are confusing me. Can you please mute yourself? I keep muting you, but you people keep coming up. Okay, I think I've done something that will not allow you to mute again. Okay, thank you. Like I was saying, what I have here, primary, secondary, and tertiary, increasing rate of dehydration. So primary has the least reactivity order, followed by secondary and followed by tertiary. So tertiary has the highest rate of dehydration. And I believe the reason why, I know you have heard of CSF rule before, because the tertiary alcohol, by the time it dehydrates, we give an alkene that adds more substituents on it, more substituted alkene than that of primary. And that follows the CSF rule that the more substituents a carbon-carbon double bond possesses, the more stable it is. So because it gives a more stable carbon-carbon double bond species, that is why there is increase in rates of dehydration towards the tertiary alcohol. Like what we have here for this reaction example we have here, for this secondary, you can see that it adds two methyl group attached to this example. Whereas if it had been a primary, it will have only one. So that means the more the substituents on the carbon, the two carbon carrying the double bonds, the more substituents on them, the more stable they are. And so that follows the CSF rule. So secondary and tertiary react as using the E1 mechanism, whereas the primary alcohol reacts by using the E2 mechanism. So this is the mechanism of the reaction. For the first one is a tertiary reaction. So we have proton transfer to the sulfuric acid, and then you now form a good living group. This is a protonated OH, which is a very good living group. So it goes off, and when it goes off, what we have is that it goes off in the second step of the reaction, and then you form a carbon ion. This second step is the rate determining step. How you know a rate determining step is when the slowest step, any step they write slow on is the rate determining step. So the second step, whereby the living group, the protonated OH, goes off to form the carbocation, is the rate determining step. And so this is the living group, which lives as water. And then the third step is the addition of taking off of the proton by the conjugate base, which is HSO4. It picks up the proton on one of the carbon, and when it picks it up, then we now form a carbon-carbon double bond. So as it is written here, proton of the oxygen atom of the alcohol converts a poor living group, OH, into a good living group, which is a carbon ion. And this step is a rate determining step. We can also call it a rate limiting step. Either of the two is correct, rate determining step or rate limiting step. So it involves bond cleavage. Of the bond cleavage, you can see with this red arrow, it is cleaved here. And then a base, such as HSO4 or water, removes a proton, removal of proton from a carbon adjacent to the carbocation, and the electron pair of the carbon-hydrogen bond is used to form the new pi bond. So this is the reaction mechanism of dehydration reaction of a tertiary alcohol. And if you look at the products, of a tertiary alcohol, if you look at the products, you see that the product is giving us two carbon and methyl group, and it is of course going to be more stable. There is also what can also happen is what we call carbocation rearrangements. When we have carbocation, there is always the tendency of the carbocation rearranging itself in such a way that it forms a more stable carbocation. And I've told you that the most stable cation is always the one that has the highest number of alkyl group or substituents around it. So when carbocations are intermediate, a less stable carbocation will be converted into a more stable carbocation by a shift of hydrogen or an alkyl group. So this is a rearrangement reaction. That's just like I said. So this migration group is a 1-2 shift with 2 bonding electrons, and the carbon it leaves behind now has only 3 bonds, 6 electrons, giving it a net positive charge. So if we look at the example we have here, there's a shift of this R to this. This is a 1-2 shift, a carbocation rearrangement. And if we are able to see the whole molecule holistically, we'll be able to know that the shift is towards a more stable species of the carbocation. So that means it is more stable. So this is less stable, and so it shifts to form a more stable one. The movement of hydrogen atom is called a 1-2 hydride shift. A movement of an alkyl group is called a 1-2 alkyl shift. So it tends to form carbocation rearrangement in order for them to move from a less stable carbocation and to form a more stable carbocation. And that's always occur at the second stage, this second step. You know, we have a carbocation in there. So if this is already stable, but if it is not stable, and what makes it less stable is maybe if it has, if the carbocation, it doesn't have 2 alkyl groups in it. Even sometimes the alkyl group can shift. So it always occur at the second stage. It can happen. And then it shifts to a more stable one that can form a more stable carbon-carbon double bond. So these are examples of the 1-2 shift. So this is a secondary alcohol reacting with a sulfuric acid, and then we have the proton has been taken away. The proton is taken away. Then we have this is the leaving group. The leaving group is always the water. And when this break off, you have, this is the carbocation we are talking about. So the carbocation has been formed in step 1 and 2, like I showed you the other time. This is the carbocation that has been formed in step 2. You know, step 1 and 2 that I showed you, let me show you again. Is this step 1 and 2 are what are condensed together now. This step 1 is the attack of the sulfuric acid to form the good living group on it, which is water. And step 2 is the removal of the living group. So let's go back here. You see that this is it. So step 1 is the attack of the sulfuric acid, and the step 2 is the removal of the living group to form the carbocation. So at the end of the step 2, you have the carbocation. And like I said, this step 2 that we have the carbocation is actually when the rearrangement can occur. So this is the arrangement. So it has shifted from this to here now. So it's shifting from this carbon to this carbon. You can see the red lines. Let me expand it a bit. So it's shifting from this carbon to this carbon. Shifting, this is an alkyl, 1-2 alkyl shift, because it's a methyl group from one carbon to the adjacent carbon. And when that happens, it converts the secondary carbocation to a more stable tertiary carbocation. Now, if this one shifts, now you can see that where we have the tertiary, where we have the carbocation is now what? Compared to this one, where we have the carbocation here is a secondary carbocation. Whereas where we have the tertiary carbon here is a tertiary one. And like I said before, that the tertiary carbocation is more stable than the secondary, and the secondary more stable than the primary. That is Sesev rule. You can go and check it out. It's Sesev rule. So this is a more stable carbocation. So it shifts, it's shifted. And so the last step can then occur after the shifting. Then you have your alcohol and you have your alkene at the end of the day. And so that is so this is the alkene we now have. You can see that the alkene we have now, all the 2 carbon are carrying alkyl groups. They are carrying alkyl groups because the last step is always the loss of hydrogen that is taken up by the base, the conjugate base. So this is a very, very stable alkane that is formed. And that is why the carbocation rearrangement occurs. So then that's what we call the iodoform and the aldoform reaction of alcohols. This is also one of the tests that is used to test alcohols in the lab. We are going to do this test also when you come for practical classes. You are going to do it in the class, in the practical class. The aldoform, you can call it the aldoform reaction of alcohols or the iodoform. So alcohols which contain the group that we have here, that is, there's a CH3 that is attached to the carbon carrying the OH. That is what we mean. That is alcohol that contains methyl group attached to the carbon that is carrying the OH. Please note it. The carbon that is carrying the OH must contain OH, that's CH3. It must carry CH3. CH3 must be linked to it, must be attached to it. Another group can be here in this R, but be sure that CH3 is attached and hydrogen is also here, then H. So this R can be anything. So for such compounds like this, whereby we have one R attached to the carbon, we have OH, we have CH3, and we have hydrogen, the aldoform reaction is possible. So such as ethanol, you know, ethanol is CH3, CH2OH. You have ethanol and propan-2-ol. This is propan-2-ol. They give a pale yellow precipitate of iodoform is formed. This is iodoform, CHI3. And what does that mean? That means that iodoform is going to replace some things there. So when warmed with a mixture of potassium iodide and excess sodium chloride, which is also called sodium hypochlorite solution, or with iodine and sodium hydroxide, you can use so many reagents to form your iodoform reaction. We are just mentioning the so many ways. But although in the lab, we will have already added the iodoform, so you just give it the reagents to use, but you can add it together by yourself. So this is done because under the mild oxidizing condition, this type of alcohol group is converted to ketones. They are converted to ketones. So this COH will now be converted to C double bond O. They are converted to ketone, which can undergo iodination and cleavage, giving a triiodomethane as a product. I will show you in the next thing now. So this is the iodoform reaction now. So when you have this compound here now, this can be CH3. If it is CH3, then that means the primary alcohol, maybe 2-propanol. So when you react it with this sodium, this oxidizing, it's oxidizing agent. It's similar to what we use. These hypochlorites and all these compounds are similar to what we use in bleaches, because they're oxidizing agents. So when it occurs, it forms a ketone. But then that's the reason why there must be CH3 is because these 3 hydrogen are being displaced by 3 iodines, because you can see that we have 3 iodines there. That's why it says that the carbon carrying the OH must have CH3, because the 3 hydrogens will be displaced by iodine. And so you have this. That is the oxidation reaction. Then the halogenation occurs in such a way that when this reacts, if it is a ketone can also react and can also form iodoform reaction, especially when it is like propanol, as long as it contains CH3 that is attached to the carbon carrying the carbonyl functional group, it can also occur. So iodoform can also be done for halogenation. So the first one is for alcohol, the second one is for ketone. And then what you have, this ketone here, the intermediate products can then cleave to now give us sodium ethoxide or sodium carboxylate anyway. So then yellow precipitate, this is not the yellow precipitate that is formed at the end of the day. It will occur like that for this one too, that there will be a cleavage. When sodium hydroxide is added, you have what you have here. A yellow precipitate will be formed, which is the iodoform. This is the iodoform, you get it. And that is it. So it's a test that is used to also identify alcohols in the lab. You are going to do that in the lab. You understand it more when you get to the lab. I think that is the end of alcohol reaction. In the next class, I think I will finish in the next class. I'm trying to, so that I finish on Thursday what I have to teach you. But for now, that's the end. Please, you can raise up your hand if you have a question, so that in case something is not clear, you can raise up your hand so I can. I'm not saying you should talk. I say if you raise up your hand, I will see your hand raised up on my screen. I can then call you. Everybody should remain muted. If you have a question, just raise up your hand.
Please, 120. Follow me. Oh, too sorry.
So that is chat. What are you saying? Many of you will say you are in class and you'll be doing so many other things. You will not be listening to the lecturer. You will just be in class to mark attendance. You'll be doing so many other things. And so many of you are not listening to me. You can see the example I just listened to now. They were fighting there. They're arguing, making noise. And you still say you are in class. It's better you know what you have to pass this course to their next level. And you can only get that when you pay attention, when you attend class and you pay attention in class. So that by the time you want to do exam, you know the right answers to put down. If you don't listen to the lecturer, how do you intend to get information and knowledge on a particular topic? I'm still waiting for people that will raise up their hand. And if there is no question, there may be I will call the class, the internet problems is that out of my reach, it's beyond me, but I'm happy that I'm able to finish the class for alcohol. So have a nice day. If you don't have any question. Bye-bye. I believe you all wrote your names. Yes. I will pick your this thing from, yes, thank you very much. I pick your attendance from my